The animations that we've shown up until now all relate to a single fluid, and one of the things that is extremely important to connect is that the pressure accumulation or the weight accumulation that results in pressure is different in different fluids or in fluids with different properties. And what we're going to show here is the effect that happens if you've got a denser fluid, the one on the left, and a less dense fluid, the one on the right. What could cause this density difference might be that the one on the left is saltier than the one on the right, so that it's got a higher concentration of solutes within it. It might be that this is colder than the one on the right, so that this expanded fluid on the right is associated with being warmed, and that might result in this temperature difference that we sometimes get on the surface of the Earth caused by differential heating. Clearly what's going to happen is the accumulation of pressure is different in the two different sides of this system. So it's a rapid or a steeper slope to the pressure accumulation in the denser fluid side than it is on the less dense fluid side. And I think we can probably see fairly easily what's going to happen as we allow the system to run. So if we open the stopcocks, then we get this communication of flow that takes place. Initially what happens, of course, is the dense fluid floods underneath this lighter fluid and begins to lift it. And it's interesting how gravity, which is a downward force, can cause upward motion. In fact, it's probably almost as common for gravity to cause something to move up as to move down when we have fluids that have different properties. As this begins to lift, we get an interesting connection that we haven't seen before. That is that the lighter fluid begins to flow from the right to the left. As we complete this circuit, there's a pressure difference that causes the lighter fluid is actually having a higher pressure than the denser fluid above the level of the denser fluid in this particular case. And so we produce now for the first time a cell, a communication cell, where the flow is somewhat circular in its motion. Denser to lighter in the lower part, lighter to the denser side in the upper part of this chamber. If we allow this animation continue, this buildup continues as well. And as the levels begin to be more uniform, there begins to be less communication. We'll let that run one more time and stop it as it reaches the end. So we have the denser fluid inducing the rise in the less dense fluid, causing the two fluids to move at the point when they reach equilibrium. We have a communication that takes place that causes the flow to cease. And we'll try to stop that right at the end in this case. So at this level now we've reached pretty well an equilibrium. One step further and we'll reach the equal levels in both sides of this container. What we have at that level is an interesting thing. We have the lighter fluid on top of the denser fluid. And that is in fact the only structure that's stable with respect to this fluid system. That only when the lighter fluid is a horizontal layer above the denser fluid do we have a stable structure. And that's going to be of great significance to the Earth because in the tropical regions where the ocean is warmed on the surface, we tend to have a lighter fluid over the dense fluid, which produces extreme stability. In the Arctic region, where the upper level is being cooled, and particularly where it gets an injection of high salt solution from freezing ice, then we get a denser fluid above a lighter fluid, which is intrinsically unstable, and the denser fluid will plunge through the less dense fluid and induce a change or a turnover in the flow that wouldn't be possible in this stable structure that we've shown here. So this is now when we've almost approached equilibrium and the denser fluid is entirely below the less dense fluid. We're now going to complete the set of representations that we've had, these animations that show pressure and density differences and that result in different flow by showing one other configuration. And this other configuration, of course, takes place when you have a differential heating effect that's more explicitly shown in our diagram. And so we're going to start with two different fluids. We're going to assume that they're quite dense and that they're quite expansive as we heat them. And we're going to sort of, figuratively speaking, sort of bring in a heating process into this mixture. The two sizes of fires are sort of showing in a kind of symbolic fashion the fact that the right side's being heated much more than the left side. Of course, the sense of this is not that this is necessarily a fire or that it would be as dramatic or as quick as this, but we could imagine, for instance, that the right-hand side is land that's fairly dry and the left-hand side might be an ocean surface that's fairly wet, and the air above that is in contact with that surface. Because photons absorb much more deeply within a fluid, there's a greater level that's heated by solar radiation. In addition, there's a higher specific heat to this, and in addition, the ocean would have evaporation or evaporative cooling, so that the cooling would be, or the heating would be much less intense on the ocean than it would be on the land. As a result of this difference, we get this accumulation of warming that takes place more rapidly on the right side than on the left side. And we're going to show that here is this idea that the fluid on the right hand side becomes more rarefied and lower in density than the one on the left hand side. This is, of course, highly exaggerated and purely conceptual in terms of its orientation, but it is going to produce something different for us, that there is quite a different rate of accumulation of pressure on the left hand side than the right hand side. The cooler or the denser fluid on the left hand side has a larger pressure at the bottom of the system than it does in the other case, and we have a significant difference with respect to the pressures at the top as well, so that we've got a higher pressure on the right hand side than the left hand side at the upper levels, and a lower pressure on the right hand side than the left hand side at the lower levels. And of course, when we cause these two vessels to communicate, then we produce for the first time a truly convective cell. That when we open this up, we get this simultaneous flow in two different directions. And the flow is going to be, of course, from left to right on the bottom and from right to left on the top. And so we get, again, that circulation pattern, in this case driven not so much by the fact that the two fluids are of different nature, but in this case very explicitly driven because of two different temperatures. And this convective cell, as it's called, that's formed as a result of this differential heating, can take place on the Earth in a whole variety of different ways. We get a land breeze and a sea breeze that takes place because of differential heating between, say, an island and the ocean around it. The ocean is warmed much less than the land, and so during the daytime we get this onshore breeze that brings in this cool air from the ocean into the land and brings this cooling effect. At upper levels we have an outflow taking place. At night the situation is reversed, where the land cools off much more rapidly than the water, and we get a flow in the opposite direction then as a result of that exchange, and we get a sea breeze that takes place, or a breeze that leaves the land to the sea. We also get the same effect associated with things like a monsoon over the Indian subcontinent, where you get a much larger cell being formed as a result of the much more intense heating and cooling that takes place over the land compared to what takes place over the water. And we get this monsoon season that takes place between summer and winter over this Asia and Indian subcontinent in the Indian Ocean. We also, of course, get a differential heating cell that's much more persistent, that takes place over the ocean and over the land as a result of the difference in radiative input between the tropical regions, which have intense warming, and the more temperate regions, which have less intense warming, and we produce large cells, and that's what we're going to look at next. But let's just let this run out a little bit and see how that convective cell tends to move again towards the same kind of equilibrium that we had before, this one characterized by the lighter fluid again, or the warmer fluid in this case, on top of the colder fluid. And again, that is the only stable configuration. And what we need to look at next is how this whole animation comes to life in the way the Earth has a circulation pattern of its atmospheric system. And that's the last thing we're going to try to achieve in this week.